Hi everyone, my name is Yifan. It's my honor to give a presentation with my partner Qinzi on the exciting work we did with Professor Tseng at Boston College. Our research is about reaching approximate consensus when every node may crash. So to give a brief summary, there are n nodes in our model, and we want to achieve approximate consensus. It is important to note that the model is asynchronous, and we assume eventual communication in delta units of time, as this will be important for later proof. At most, f of them may crash forever, and once a faulty node crashes, it cannot recover nor send or receive messages. The rest of them have uptime and downtime, and may crash for infinitely many times. During uptime, the nodes can send and receive messages, but not during downtime. We also assume that each node has a limited size persistent storage, so that data stored inside the persistent storage will never be lost. So when nodes recover, they can retrieve data from the memory. However, we want the size of persistent storage to be as small as possible. Because of this limited size assumption, we cannot simulate priori algorithms. And here's why when we take a closer look at our models. Usually, the traditional model has a reliable channel, which is shown in graph A. So assume I send a message, it will always be delivered if the destination is correct. But for crash recovery with a reliable channel, as shown in graph B, the message will always be delivered, but it will still be lost during downtime. And by contrast, in our model in graph C, there is no guarantee that the message will be received, and the data can be lost during downtime as well. In order to simulate models A and B, you need to remember everything, since we do not know the network delay. In conclusion, with only limited size persistent storage, we can never simulate a reliable channel under our crash recovery model with fair lossy channel. And that's the key challenge for us. Besides, we want to find out how much storage space we need. As a result, we devised a novel algorithm that only stores 3 things. We will present a simple algorithm that solves approximate consensus under the condition n greater or equal to 2f plus 1 under our crash recovery model with fair lossy links. In our algorithm, each node I stores 3 variables in its persistent storage. The first variable is the phase number pi, which is an integer. I need to point out that under the asynchronous setup, different nodes might be in different local phases at the same real time. For example, if the communication between node A and other nodes are very fast, node A might proceed to phase 10, while another node B still stays in phase 0. The second variable is the local state Vi, which is a float. We assume that the input of all nodes are bounded in a certain range from 0 to k. The third variable is an n-bit message counter, Ri. Each bit is either 0 or 1. Ri is stored in a vector form, and the jth element of Ri represents whether node I has received a message from node J in a certain phase. If the jth element is 1, then I has received from J, and vice versa.
In our algorithm, initially, each node I initializes its state to pi equals to 0, its local state to vi equals to xi, where xi is the input of I, and its message counter Ri to an almost everywhere 0 vector of length n, except that its ith element is set to be 1. When the algorithm begins to execute, each node repeatedly broadcasts all its local state and its phase number to other nodes. In practice, we can set the frequency to be broadcasting every 50 milliseconds. For each node I, at the beginning of phase pi, it resets its message counter Ri to a 0 vector of length n, and then sets Ri of I to 1. Every time when I receives a message V and P from another node J, it checks the phase number P of the received message. If P is higher than Pi, then node I directly copies the received state and jumps to that future state phase. More specifically, node I updates its local state to Vi equals to V and updates its phase to Pi equals to P. Otherwise, If the received phase number P equals to the phase number Pi, then node I checks whether it has already received from node J in phase Pi. If the J's element of Ri is 1, in other words, J has already been received, then I just ignores this message. Otherwise, if it's 0, then node I updates its local state from Vi to Vi plus V. Also, it updates the message counter by updating Ri of J from 0 to 1. When node I received at least n-f messages of the same phase, in other words, when the size of Ri is greater than or equal to n-f, then it proceeds to the next phase. More specifically, it updates its phase to Pi plus 1, and then updates its local state to Vi over the size of Ri. The reason of dividing Vi by the size of Ri is that node I is taking the average of all the received messages as the new state. Although the intuition behind our algorithm is simply aggregating and averaging all received messages, there are two novel differences between our algorithm and previous ones. First, our algorithm allows each node to directly jump to a future state if it receives a message in a higher phase. The reason why each node can simply copy a future state is that the local states in higher phases must fall in a narrower range, and we will prove it later. The phase jumping process also solves the potential problem that the phase gap between any two nodes might be arbitrarily large due to the asynchronous setup. And this might also potentially speed up our algorithm. Second, each node aggregates its new state by directly adding the received state to its current state. And at the end of each phase, it computes the average value of all received messages by simply dividing the latest local state by the size of Ri. This allows each node to store fewer values in its persistent storage, because now each node can simply store a vector of n booleans as its message counter, instead of storing a vector of n floats. Now we will present the proof structure of our algorithm. First, termination is satisfied because our eventual communication assumption guarantees that every crash-prone node will eventually receive enough messages to proceed to a higher phase. Also, validity is easy to see because we only consider crash failure. So either copying a future state or taking average of local states guarantees that the new state will fall in the range of the inputs. The hard part is the epsilon agreement of our algorithm. The intuition is that the range of local states shrinks in every phase, and this can be proved by induction. Here we only present an intuitive proof of the induction. So consider a node I in phase P, and we assume by induction that any state in phase P plus 1 or higher is in a narrower range. Our goal is then to show that the new state of node I in phase P plus 1 or higher is also in that narrower range. By our algorithm, there are two methods for node I to proceed to a higher phase. The first method is copying a future state and jumping to the future phase. In this case, we can simply prove that the new state is also in the narrower range because a state is just a copy of the future state, and which is also in the narrow range by our induction assumption. Now, let's consider the second method. The second method to proceed to the next phase is taking average of n-f phase P messages. We can prove this case with the common value analysis. Under the assumption that n is greater than or equal to 2f plus 1, we can induce that n minus f is greater than n over 2. So as the graph shows, we can always split the set of all phase P local states into two halves. Let's suppose that the minimum value of all phase P local states is A, and the maximum value is B. And also, let's define the middle value as half of A plus B. Then we can split the set of all phase P local states into the lower half and the upper half, depending on whether a state is greater than or less than the middle state. We can observe that either the upper half or the lower half must have size which is less than or equal to n over 2. And we can assume that the size of lower half is less than or equal to n over 2. And the other case is symmetric. So in this case, it is guaranteed that no node can receive messages only from the lower half, because n minus f is strictly greater than n over 2, which is further greater than or equal to the size of the lower half. We present a simple example to illustrate the proof. So in this example, we assume that n is equal to 5 and f equals to 2. In a certain phase P, 3 of them have the local state 1, and the other 2 nodes have state 0. In this case, the lower half is the 2 zeros, and the upper half is the rest 3 ones. The size of lower half is 2, and this is less than n minus f, which is 3. We can check that it is possible for some nodes to receive all 3 ones. For example, as the next picture will show, the 3 blue nodes are all from the ones. However, any node can only receive at most 2 zeros among any n minus f messages.
We also have some exciting prospective work. For example, we can find different protocols that solve consensus under Byzantine failure. In that case, we can devise an algorithm with racing processes that's similar to the algorithm we have right now. Besides, we can try to prove the lower bound of space complexity. And anyways, the fundamental question that we want to ask is what tasks we can solve with limited space complexity. And that's all. Thank you for listening.